this triangle, we use the sine ratio to obtain this equation. Now to solve it, we just move the terms and calculate. Now, we can see that x is approximately 11.77. It's that easy.
That's great. Thanks a lot, Ringo.
That reminds me, I have to prepare for my next lesson at school. It's about trigonometric ratios.
I have an idea. Why don't you use your video camera? You could shoot some video segments to use as teaching support. With some lively video segments, your lesson would be a lot more interesting.
That's a good idea. But I'll need you to help me.
That's no problem. And you know what? I was thinking that we could ask some other people.
Today's lesson is about trigonometry. The word trigonometry comes from two Greek words. The first means triangle. The second means to measure. In fact, one of the main concerns of trigonometry is the study of the calculation of the sides and angles of a triangle.
Okay, action!
The fundamental concept of trigonometry is trigonometric ratios. So what are trigonometric ratios? The flagpole over here is very tall. I couldn't really climb to the top to measure its height. So how can I find out how high it is? It's not a difficult problem to solve. We can make use of the shadow of an object. We first measure the length of the shadow of the pole. Then we place a much shorter rod on the ground and measure its height and the length of its shadow. Since the angle of the sun's rays projected on the tall pole is the same as those projected on the short rod, these two triangles are similar. By the similarity of triangles, the corresponding sides of these triangles are proportional. So the tall pole's height is equal to its shadow length multiplied by the ratio of the short rod's height to its shadow length. This ratio of two sides of a right-angled triangle is called a trigonometric ratio. Its value is related to the size of the acute angle of the right-angled triangle. For example, if the angle of the sun's rays projected on the rod changes, the ratio of the rod's height to its shadow length changes. In order to find the trigonometric ratio's value, we just have to know the angle of projection of the sun's rays.
We've been filming the whole morning. Even so, we haven't started with the main topic.
The next objective is to introduce three common types of trigonometric ratios. Right, look here.
Okay.
Say, Lewis, can you describe the three different types for me?
Yeah, sure. In a right-angled triangle, let's suppose this acute angle is theta. This side is then the opposite side of theta. This side is the adjacent side of theta. And this is the hypotenuse. For these three sides, when we use any two for comparison, we'll obtain a trigonometric ratio. For instance, comparing the opposite side with the hypotenuse gives us one of the trigonometric ratios. This trigonometric ratio is called the sine of theta, written in short as sine theta. Comparing the adjacent side with the hypotenuse gives us another trigonometric ratio. This trigonometric ratio is called the cosine of theta. It's written in short as cosine theta. Comparing the opposite side with the adjacent side gives us the third trigonometric ratio. The third trigonometric ratio is called the tangent of theta. It's written in short as tangent theta.
Yes, that's correct.
Yeah, but there's something I'm not sure about. Of course, we can work out the values of trigonometric ratios on a calculator, but how is the actual calculation done?
The precise value of the ratios are calculated using maths at a higher level. Approximate values can be worked out more easily by a graphical method. This is the way to do it. On graph paper, we draw a circle with a radius of 1 unit. On the x-axis, we have a radius OP. We then rotate OP around the center O in the counterclockwise direction through an angle theta. From P, we drop a vertical line PQ to the x-axis. This gives us the right-angled triangle OPQ. In this triangle OPQ, sine theta equals the ratio of the opposite side to the hypotenuse, which is PQ divided by 1 equals PQ. That is to say, sine theta equals the y-coordinate of the point P. If the angle theta is 15 degrees, sine 15 degrees roughly equals 0.26. If the angle is 30 degrees, sine 30 degrees roughly equals 0.5. If it's 45 degrees, sine 45 degrees roughly equals 0.71. If it's 60 degrees, sine 60 degrees roughly equals 0.87. If it's 75 degrees, sine 75 roughly equals 0.97. From the diagram, it can be seen that as angle theta increases, sine theta also increases. When theta approaches 0 degrees, sine theta approaches 0. Conversely, when theta approaches 90 degrees, sine theta approaches 1. Therefore, the values of sine theta lie between 0 and 1.
That's how the values of the sines of angles are worked out. Can we use the same method for other trigonometric ratios?
That's right. The cosines and tangents of angles too are worked out with this method. Let's take approximate values of cosine. Cosine theta equals the ratio of the adjacent side to the hypotenuse, or QO divided by 1. Therefore, cosine theta equals QO equals PR. These are the approximate values of the cosines of various angles. From the diagram, it can be seen that when angle theta increases, cosine theta decreases. When theta approaches 0 degrees, cosine theta approaches 1. Conversely, when theta approaches 90 degrees, cosine theta approaches 0. Therefore, the values of cosine theta lie between 0 and 1. For the approximate values of tangent, we draw a vertical line from the point S perpendicular to the x-axis. We then extend OP to meet the vertical line at T. This gives us the right-angled triangle OTS. Tangent theta equals the ratio of the opposite side to adjacent side, which is TS divided by 1 equals TS. Therefore, tangent theta equals the y-coordinate of point T. These are the approximate values of the tangents of various angles. From the results, it can be seen that when angle theta increases, tangent theta also increases. It may even be greater than 1. When theta approaches 90 degrees, the value of tangent theta is very large. So now that we've made clear what exactly we mean by trigonometric ratios, let's look at some applications.
Good idea, and I can help.
What are you doing here?
Hey, Ringo!
Hi there. Where are you going?
Good to see you. Hey, I'm designing a new shopping arcade. I'm going to see the client about the staircase design.
Oh, well, you know, I'd be interested in seeing your design.
Sure, I'd like to get your opinion. I have it here. Wait a minute, I'll get it out for you. Hang on.
I see.
There you go. As you can see here, this is the staircase design. It comes straight down here from the upper gallery.
I see. It looks too steep. You may have safety problems. Maybe you should modify it.
You think so?
Yes, but no problem. I was thinking of this. Look. Split levels. Don't you think that's much better?
But if it's modified, what's a decrease in the inclination?
I'll work it out for you.
Great. Take this. It's all yours.
Right. In the first diagram, to obtain the angle of inclination, we'll use the ratio of its opposite side to its adjacent side. That is its tangent ratio. So tangent theta equals 3 over 4.5. So 3 divided by 4.5, then equals, then inverse, then tangent. And we get an angle of inclination of approximately 33.69 degrees. In the second diagram, and using a similar method, we obtain tangent phi equals 0.5. Using the calculator, our new angle is roughly 26.57 degrees.
The angle of inclination in my design is 33.69 degrees, and this angle is only 26.57 degrees. Quite a difference.
Well, just think it over. The stairs will be much easier for older people or those who have difficulty.
Yes, you're right. Hey, I'd better be going. I'm running late. Hey, look, thanks for your help, really. See you again.
Okay, yeah, no problem. Good luck.
Okay.
Give me a call.
Bye.
All right?
Bye.
See ya. Now that we're out of the city, why don't we have a rest here?
Hey, Ringo.
Huh?
There's a road sign with a 1 and a 10 on it. What does it mean?
That sign is used to show the gradient of the road. The 1 and the 10 mean that when the horizontal distance between 2 points on the road is 10 units, the vertical distance is 1 unit. Well, we'd better get going. We have to see Uncle Bill, and it's a long way. Should we go?
Sure.
Well, we've come to the end of the road. The meter shows we've traveled 1,000 meters, so if the gradient's 1 in 10, what's the height of the starting point from here?
Are you trying to catch me out? Now then, it's quite an interesting question. The gradient of the road is 1 in 10. Let's call the angle of inclination theta, so tangent theta equals 1 to 10. So the angle of inclination is roughly 5.71 degrees. The length of the road is 1,000 meters. We'll call the height of the starting point h meters, so h over 1,000 is the opposite side to the angle of inclination over its hypotenuse. It's therefore the sine ratio of the angle of inclination, so h roughly equals 99.49 meters.
It's just down here.
There's nobody inside.
I know. I guess he must have gone out.
Hey, look, there he is. Uncle!
Hi, Uncle!
Oh, Ringo. Hello, Lewis.
Hi there. We thought you went to town. We were just about to go home.
I was just in the village. I've been buying some land. I've the plans here.
Really?
The plot of land is 1,100 square meters.
Really?
Can you calculate it for me to see if it's correct?
Don't worry, it won't be a problem.
Oh, thank you.
First of all, I'll divide the land into a right-angled triangle and a right-angled trapezium. For the right-angled triangle, we'll take the side opposite to this angle to be x meters long, and the adjacent side y meters long. The ratio of x to 35 is the ratio of this angle's opposite side to the hypotenuse, that is, sine 70 degrees. Therefore, x equals 35 times sine 70 degrees, which is roughly equal to 32.89. Similarly, y equals 35 times cosine 70 degrees, which is roughly equal to 11.97. So the area of the triangle equals 11.97 multiplied by 32.89 and divided by 2, roughly 196.85 square meters. Next, we'll calculate the area of the trapezium. The lengths of its upper and lower bases are known. What is the length of its height?
Let me give you some hints. What is the size of this angle? And the size of this angle? What is the length of this line segment? How do we calculate the height of the trapezium? Is the land really 1,100 square meters? Cut.
Okay, good take.
You guys should be in the movies.
I thought you were pretty good too. And thanks a lot, Eric. You did a great job behind the camera and acting.
Oh, it was a pleasure. I had a great time doing it.
You know, Ringo,
Huh?
I have no idea at all of the answer. I'm not kidding either.
Oh, well, let's back up and I'll explain it at home.
Okay, thanks.
Good deal. Come on, we'll go.
All right.